Bing bong. I feel like a little baby. welcome back. Welcome back to Sequences and Series Make Sense, actually. And today, we're getting a little bit funky. I've said that about a lot of series at this point. I said that about the comparison tests, but I was lying. Those series were basically simple series, and we were using that. We were abusing the fact that they look kind of like stuff that we know how to deal with in order to make these funky series less funky. Today, there is no avoiding the funk. Today, we have to look at series that don't follow the molds of like a p-series or a geometric series and have like weird mixtures of all of these lumps that we have to sort out. And we have to abstract even farther than we did in the comparison tests. This is the ratio test. So what if we come across a series that has like parts that we just don't know how to deal with? Like what if we had the series, I think it can't start at 0. This one starts at 1. Of 10 to the k over k factorial. First of all, what the hell is factorial? You might not have heard of factorial. If you've done math team, you've definitely worked with factorials a lot. K factorial means that it's every number lower than k multiplied together. So like 5 factorial equals 5 times 4 times 3 times 2 times 1, which is 120. And those are a little bit scary, because that's a lot of numbers you have to multiply. But they're super cool because they can cancel out a lot of stuff when you divide. And that'll make some of your algebra at the end a little easier. But hopefully you know what factorials are. And hopefully you see how that's not really compatible with our 10 to the k. I used k's and n's. We're going to pretend that this is a k. Our 10 to the k, well, that's not really something we know how to deal with on its own either. We don't know what to do with n's or k's in the exponent unless it's this geometric series, unless our ratio is less than 1 and everything is raised to the k. But since only part of this is raised to the k, and the rest of it is this factorial that we don't even know how to deal with, we're going to have to look at something new. So in the comparison tests, we abstracted, which is like ignored scary stuff and made it simpler, by trying to compare it to one of the simple basic tests that we know about. And we're going to be doing something similar with abstraction, where we look at just the most important parts of what we need. Like, what makes a series converge? Well, if the ratio between each term gets smaller and smaller, then our terms are going to become more and more insignificant and thus add together. Like, that's the principle that makes a geometric series where the ratio is less than 1 converge, right? Because if it's 1/2 and 1/2 of 1/2 and 1/2 of 1/2 of 1/2, etc., it's going to get really small. And that works because the ratio between the terms is less than 1. And so what if we look at this and say, OK, we know this isn't a geometric series. We know we can't compare it to a geometric series because it is just too funky. What if we look at the scale of infinity? Again, all of this is just working with the scale of infinity. What if we pretend it's a geometric series when it gets really, really, really far into the future? Or far into like numbers? What is the ratio between the terms? Once we've gotten really far into infinity, what is the relationship between the terms? And like a geometric, like at some point, will this basically on the scale of infinity, become a geometric series with this ratio between terms that is consistent? And we can do this by looking at the ratio between terms. So what is from one term to the next term the ratio? So in a series, in like a geometric series, you'd take one entry and divide it by the entry before that, and you'd get the ratio between terms. And we're going to do that again here. So if we say that this series is a sub n, then we want to take the ratio between terms. So a sub n plus 1, right, the next term divided by the current term. Then the ratio test has one other element. It can be either positive or negative, right? We don't care if the ratio is negative, which just means that it's going to be like an alternating series bouncing back and forth, but the ratio is still small. Like, it doesn't matter in a geometric series if the ratio is negative. It just means it'll bounce back and forth, but it'll still behave like a geometric series. So if the absolute value of our ratio between our tests approaches something like a geometric series that converges. So if we go the limit as n approaches infinity of the ratio between terms, if this is like a geometric series less than 1, then our series converges. Because on the scale of infinity, it's like a geometric series with the ratio less than 1. If it equals 1, that doesn't necessarily mean it diverges. We just can't tell what it's doing. And if this limit is greater than 1 or goes off to infinity, then of course it doesn't converge, because that means each term is getting bigger and bigger, and we don't like that. So we can use this, right? Like this, it might seem kind of complex. Like that's a big fraction. But when we have things like this specifically, when we have n's or k's in the, oh my god, I use an n and a k interchangeably again. Don't mind me. If we have k's in the exponent, n's or k's in the exponent, then this division gets super clean. And if we have factorials, then this division gets super clean. So anytime you see this or this, you should maybe think to use the ratio test. And let's run this through the test. Let's see if it works. So I'm gonna do it under here. If we want the limit as n approaches infinity of our next term, a sub n plus 1, or in this case, I'm going to use n's. I don't know why I used k's. It's because the AP Classroom video used k's, and it's really throwing me off. They are interchangeable, though. You should know that. 10 to the n plus 1 over n plus 1 factorial. Note that you can't distribute the factorial. That's not how it works. And then instead of dividing it like it's a big fraction, I'm going to do fraction division and multiply by the reciprocal, which often makes this cancellation look really easy. N factorial over 10 to the n, which is just our original thing, and I'm flipping it upside down because it's division. And now, this has a lot of simplification that can be done to it. This is 10 to the n, or 10 to the n plus 1 divided by 10 to the n. How do you divide with exponents? You subtract the exponents when the base is the same. And so n plus 1 minus n is just 1. And so this is going to come out as, it's the same as the limit as n approaches infinity of, we've got 10 on the top, and n plus 1 factorial, if we want to go through the cancellation with factorials, I'm going to write it over here. N plus 1 factorial equals n plus 1 times n minus 1, etc. And n factorial equals n times n minus 1, etc. And you see how these cancel out super perfectly when we divide them. And so n plus 1 factorial, or n factorial divided by n plus 1 factorial, is just 1 over n plus 1 factorial, or 1 over n plus 1. So we're left here with n plus 1 on the bottom. And so see how, when we have these funky things that we don't know how to deal with, the ratio test can often make them simplify really easily. And so we've got this very simple thing, the limit as n approaches infinity of 10 over n plus 1. Now n's in the bottom, and if infinity is in the bottom, then this is going to basically be 0. So the limit of this equals 0. And then we say 0 is less than 1. And so if you think about it, the ratio between these terms is approaching 0. And we know that the terms are approaching 0, or else it would automatically diverge. That's what we can just like tell by inspection. The terms are approaching 0, and the ratio between the terms are approaching 0. And so it's like a geometric series, but there's no space between each term. This converges super well. And so you say, since 0 is less than 1, since the limit of a sub n plus 1 over a sub n is less than 1, by the ratio test for convergence, this funky little funky boy converges. So that's really good. Ratio test is really good at dealing with stuff that we've never seen before, especially n's in the exponent and factorials. And it's also super important because we can use this format, and this like limit of a fraction has to be less than 1 for the next thing we're going to look at, which is power series. So this comes back in just a second, so don't you forget it. The ratio test makes sense, actually.